Hello, this is Stokes Baker. In this video, I'd like to talk about how to perform a one-way analysis of variance using Microsoft Excel. Analysis of variance is a collection of statistical techniques that analyzes the components of variance observed in phenomena and to identify differences between groups of means. And one-way analysis of variance, also known as a one-way Anova, involves populations that differ by only one factor. An example of that would be comparing geese clutch sizes from 3 different ponds. There's only one variable, and that is location. Why conduct one-way Anova? Well, you would use that when you're comparing more than 2 means at a time. The reason why we need to do that is that if you do a multiple pairwise t-test, you actually inflate your alpha value. One-way Anova prevents the inflation of that alpha value. So to do a Anova, you would need to evaluate the assumptions. So in this case, the assumptions are random sampling, and that's determined by your experimental design. That the samples are independent of each other, and again, that's determined by your experimental design. The distribution of each sample population is normally distributed. And to evaluate the assumption, you would make a histogram or polygon to evaluate the population distributions. And finally, that you have homoscedasticity. What is homoscedasticity? Well, homo means same, scedastic refers to variation. So the variance of each sample is the same. One way to represent homoscedasticity is the variance of the first population equals the variance of the second population equals the variance of all your populations to the last population. If you do not have homoscedasticity, then we say you have heteroscedasticity. To evaluate homoscedasticity, you would do an F-test by comparing your sample with the largest variance to the population with the smallest variance. Now, in the one-way Anova, our null hypothesis is that each mean in the population is the same. So the population mean of the first observation, same as the second, so on and so forth till you get to the last one. And the alternative hypothesis is that at least one of the means is not equal to the others. In this example, we're comparing 3 geese populations from 3 different ponds. So we have population A, B, and C. And what we're going to do is we're going to count how many eggs per nest. So this goose had 5 eggs in her nest. This one had 6, so on and so forth. Since we're doing more than 2 t-tests, we're going to do one-way Anova. But to do that, we first need to evaluate the assumptions. So to evaluate the assumption of normality, I've conducted a polygon. I first created a frequency distribution table of counts and then converted them to relative frequencies. And then here's the corresponding polygon. And as you can see in this polygon, that the 3 populations are relatively unimodal and symmetrical, so we can make the assumption that normality has been fulfilled. This is also going to kind of give us an insight into who might be different, which is probably population C. The next assumption we need to test is homoscedasticity equal variance. And to do that, we're going to do an F-test. But to do the F-test, what we're going to do is we're going to compare the population with the smallest variance to the population of the largest variance. So the smallest variance is in column corresponding to population B, and largest is in the column corresponding to population A. So in our F-test, we would say F equals the variance of largest divided by the variance of the smallest. Now, fortunately, Excel does F-tests relatively easily. To do that, we're first going to go to our Data tab, click that, go to Data Analysis. In our dialog box, we have F-tests, 2 samples for variance. That's the one we're going to choose. For variable 1 range, you want to put in the population that has the largest variance. So that corresponds to population A. To do that, we're going to put in the population with the largest variance and this value right here. That would be population A. The population with the smallest variance turns out to be population B. Since I included the labels in both of those populations, I'm going to click the label button. The default of 5% is fine for alpha, and then we're going to define where we're going to do our output. I might as well put it right next to the rest of our data. And we have conducted our f-test. And again, our null hypothesis for our f-test is the variance of this largest equals the variance of the smallest. Here is our calculated value f, which is created by using that equation. And Excel does, as a default, a one-tailed test for that, but we wrote the null hypothesis as a two-tailed test. So to do p two-tail, we can use the command f test, and then we do array 1. Again, you're going to put the largest variance in array 1, but this time not include the labels. Array 2. And that is our corresponding value of P. The other way, which is I find convenient, is you can take the one-tailed test and simply multiply by 2 and get the same answer. Either way, we set alpha at 0.05, then we are going to accept the null hypothesis. And the reason for that is that P turns out to be larger than alpha. So since we accepted the null hypothesis, we can conclude there is homoscedasticity. Now the next thing to do is the analysis of variance. That's also fairly straightforward. To do that, again, we're going to use the data analysis tool pack. So click data, data analysis, and our different ANOVAs in here. We're doing single factor ANOVA. Click that. It asks you for your input range. That's all your data, including the labels and all the data. And yes, you can include the empty cells. That won't hurt anything. Click label in first row. 5% alpha is perfectly fine. And then you can define where you want to do the output. We'll put it right there. Here is a single factor ANOVA output. Just to remind you, the null hypothesis we're evaluating is the population mean, in this case of A, population A equals the population mean of B, which equals the population mean of C. So all three population means are the same. This part of the table is just basically bookkeeping, counts, sums, averages, variance for each one of our populations A, B, and C. The informative part of the table is this one down here labeled ANOVA. Starts off with sums of squares, and then degrees of freedom for variance between groups versus variance within group. Then it gives us our mean squares, our calculated value of F, and in terms of evaluating the null hypothesis, the item we're most interested in is the p-value. Now, if we set alpha at 5% or 0.05, then we are going to reject the null hypothesis. What that means, at least one of the means is different. Now, to determine which one of those means are different, we can now do all pairwise t-tests. The easiest way to do that is to calculate the probability of that t-test. And the command I'm going to use is this one, t.test. And the arguments the array, first array, second array, how many tails, and the type of test. So the arrays are your data values. So this could be the first population, the second population, A and B. The number of tails, it could be one tail or two tail. Since our null hypothesis is a two-tail test, we're going to use 2. And then we have 3 different types of t-tests. You could have a pair t-test, in which case you would type in 1. A 2-sample t-test, assuming equal variance, in case you would type in 2. Or a 2-sample t-test with unequal variance, then you would type in 3. Now, since we tested for homoscedasticity as part of our analysis, we are going to use option 2. So here is the example of the t-test I've just done. This sounds silly, but I'm doing all pairwise combinations. So I'm going to compare population A with itself. So B3 to B22 is population B. Then notice I did it twice. Comma 2 because it's a two-tail test. Comma 2 because we're assuming equal variance. Now, so I don't have to type in that formula every time, I'm going to use the click and drag function of Excel. But I'm always want to compare it to population A. So I put the $sign before the first B, before the second B, but I'm not doing any $signs over in the second array indications. Now once I've typed in our formula, yes, the probability is going to be 1. That's the same, and it makes sense. Click and drag, and then it does the other 2 probabilities. Now I can do the same thing starting with B's. Don't have to do BA again because I've done that over here, but starting with BB, I've put in a similar calculation. Click and drag, and then obviously C by itself is going to be 1. So those are different t-tests, and if you're just using alpha at 5%, then you would say those 2 t-tests are statistically significant. But remember, the reason why we did Anova is that you have the potential of inflating alpha and thus increasing your type 1 error. So to prevent that, one strategy is to do what's known as a Bonferretti correction. In a Bonferretti correction, you're actually using a more restrictive value of alpha so that when you do all the different t-tests, that the resulting composite error rate is 5%. The way you do that is use this equation. Alpha prime is our more restrictive value of alpha. It's going to be the desired value alpha. In our example, would be 5% divided by the number of combinations possible. Since we're doing pairwise t-tests, k is always going to be 2, and then n would be how many populations we're working with. So in our example, n would be 3 and k would be 2. Now to do that, we're going to use the following command. To do our Bonferretti correction, we're going to say alpha asterisk, which is our more restrictive value of alpha, equals the desired amount of type 1 error, which is 5%, that's alpha, divided by the number of combinations. Now, n is the number of populations. In this case, we have 3 populations, so n would be 3. Since we're always doing pairwise t-tests, k would be 2. Now, fortunately for us, Excel has a command that calculates combinations. The name of that command is combin, C-O-N-B-I-N, and then the argument is nk. So we're going to use this equation as our denominator And our numerator is going to be our desired level alpha, which is 0.05. And our Bonferroni corrected value of alpha is going to be 0.5 divided by 3, which gives us a value of 0.016. We will only reject the null hypothesis is that our observed p-value is smaller than this value. And yes, that's what one's true too. So both of these we still would say is statistically significant even with the Bonferroni correction. So in this case we would say population C is a different value than population A or B. And if you go look at the means, you can see that population C has a greater average than population A or B. Hope you found this informative, and have a good day. Goodbye.